Hello guys, welcome to my channel. This is Ehsan, and in today's video we're going to calculate the input impedance of these circuits from different nodes. The first circuit we're going to look at from the base, and in this one we're going to look at from the emitter and get the result at the end of this video. And we're going to use these impedances seen from different nodes whenever we want to calculate the gain of the amplifier, of different amplifiers. Okay, these are really important notes to notice that. But before we get started, if you're new here, please give me a thumbs up, hit that subscribe button, and also the notification bell, so whenever I upload a new video you'll be aware of it. Let's jump into it. So look at the first one. In this case, I'm gonna draw the small signal model of bipolar junction transistor, of this transistor. This is base, this is R pi, and here this is GMV pi in the small signal model. This is collector, and here this is emitter. So now I'm gonna add this resistance R emitter, RE, from emitter to the virtual AC ground node. So this is RE, and here this is ground. And don't forget, this is also V pi across R pi. Now we're going to calculate R in. How we can calculate it? In order to calculate any kind of resistance from different nodes, you're going to put some voltage test. We can call it VT, Vx, or whatever you like it. For example, I call this V in, and here this is I in from this voltage source, and I'm going to calculate the respect of the fraction of V in divided by I in order to calculate R in. Okay, but before, I'm going to use KVL and KCL to calculate it. Let's first of all, if you can, simplify the circuit. This is really important step at the beginning. Don't go through the circuit wildly. First look at the circuit, how we can simplify this circuit. As you can see, you can calculate the current through this R pi. It's equal to voltage across it divided by the resistance. So this current is going to be V pi divided by R pi. Okay, and now you can calculate this current, and you have this current, so you can tell me what is this current here. This current, in order according to the KCL, equals to the summation of these two currents. So it's equal to V pi divided by R pi plus GMV pi. Now I can use the KVL. This is the root for KVL. And this is the end of KVL. Why? You can't see the loop, because this is ground and this node is also ground. So I can connect these two grounds together. So this is a complete loop. Now this is here, this is the KVL. Minus V in plus this voltage, which is V pi, plus the voltage across RE, which is equal to RE times V pi divided by R pi plus GMV pi. Now, there is no I in, but here we have I in. We can calculate I in. This is I in, and this is exactly I in again. This because this is V pi divided by R pi. So here I in equals to V pi divided by R pi. By simple mathematics, you can set that V pi equals to R pi I in. Now I can substitute V pi with R pi times I in this KVL. Okay, so, and let me just simplify this. I'm gonna place V in to the right hand side. So V in equals to V pi, which is R pi I in, plus RE times V pi divided by R pi. V pi divided by R pi is equal to I in, plus GM times V pi, which is R pi I in. So here R in equals to V in divided by I in. Here this is the first term, R pi, plus this is RE times I in. I factorize I in, okay? And here we have RE times GM R pi. So what is GM R pi? GM R pi is actually beta for this transistor. What is beta? Beta is the fraction of I collector divided by I base. So here this is R in seen from this node. You can set that this is R pi plus, by some simplification, RE times 1 plus beta for this amplifier. This is a really important expression, although I proved that to you from the reference book, of course, Fundamentals of Microelectronics by Professor Behzad Razavi. But this is really important to bear that in your mind. You have to keep this into your mind whenever you want to calculate the voltage gain or the input impedance of some amplifiers, especially common emitter amplifiers or common collector amplifiers, okay? So this is important to memorize this formula. And I'm gonna set something else, because we've seen this R in from the base of this amplifier. You already have R pi from the base, okay? So we have R pi, no problem with that. But in order to drag RE and put it into the base, because the emitter current of this device is beta plus 1 of I base, in order to drag this and put it into the base, you have to multiply this resistance into this beta plus 1. So by having this node at the end, you can memorize it so easily. Now let's get through the other example. And in this example, again, I can use the same strategy. I mean that here we have this small signal model, okay, R pi, V pi, and don't forget that we don't have voltage early in this calculation, okay? So you can set that the collector is by some resistance go through the ground, and this is not important, because we only just need the current between collector and emitter. And here base is also connected to RB and then connected to the ground. And now I'm going to calculate Rx. This is important to notice that where is Rx? Rx is in here from emitter. So I'm going to put my test voltage, let's call this Vx, and call it here Ix. And I'm going to calculate Vx divided by Ix in here. So again, here we have V pi divided by R pi for this current, and we can use KCL in here in order to calculate the fraction between Ix and V pi. All of these nodes are coming into this node. So for example, here we have node A, and use KCL at node A. Ix plus GMV pi plus V pi divided by R pi equals to 0. So here we have Ix equals to minus V pi times GM plus 1 divided by R pi. Okay, so here we can set that V pi equals to minus Ix divided by GM plus 1 divided by R pi. Now I can use again the KVL from this node to this one. Okay, now use the KVL minus Vx. Here we have minus V pi, and again here we have negative RB times V pi divided by R pi, and again I'm going to substitute V pi with this expression here. So here we have Vx. Let's put Vx into the right hand side, so Vx becomes positive, equals to negative V pi, factorize this one, plus 1 plus RB divided by R pi. Now I'm going to substitute this. Let's put negative V pi in here. So by using negative V pi, this one becomes positive. Okay, so here Vx equals to Ix divided by Gm plus 1 plus R pi times 1 plus Rb divided by R pi. Okay, now by using some simple mathematics, you can let me just write it in here. Vx divided by Ix equals to, if gets the common denominator from these expressions, we can set that on the numerator we have R pi, and here we have R pi plus Rb. Okay, and in the denominator again have the R pi as the common denominator. Here we have Gm R pi plus 1, and if you all remember, this is equal to beta, and you can simplify this expression by crossing out these R pi's. So here we have Vx divided by Ix, which is Rx, equals to R pi plus Rb divided by 1 plus beta. This is the final expression for Rx. And again, because here we have to calculate the resistance from emitter node, the base resistance had to divide it 1 plus beta. So just to recap this video, and this is really important, the final expressions here, whenever you calculate the resistance from the base, you had to place the base resistance as usual plus 1 plus beta times Re, and vice versa. If you calculate the resistance from the emitter, you had to divide the base resistance by 1 plus beta. And why this is Gm? Because this is equal to R pi divided by 1 plus beta. It's again this is actually 1 divided by Gm. Okay, let's just use this one. I used the Razavi's box for the final PowerPoint here. Okay, here Razavi used 1 divided by Gm. These are really important to keep that in your mind for the calculation of the gain of amplifiers. Okay, I hope you like this video. If that's the case, please give me a thumbs up and share this video with your friend. Thanks for watching.